ICE problems. ICE stands for initial, change, and equilibrium problems. So let's look at an ICE problem. Let's say that we're going to take hydrogen and iodine and we're going to produce hydroiodic acid. And the question tells us that the initial hydrogen ion concentration is 0.5 molar and the initial iodine concentration is 0.5 molar. And it tells us that at equilibrium, the concentration of hydroiodic acid is 0.2 molar. We want to find the value for our equilibrium constant. So what we would do is we would write the equilibrium expression, fill in what we refer to as an ICE chart, and then calculate K. So the first thing we'll do is fill in our ICE chart. I stands for initial, and the question tells us that we have 0.5 molar hydrogen, 0.5 molar iodine, and it doesn't say anything about the hydroiodic acid, so that initial concentration is going to be 0. It tells us the equilibrium concentration of the hydroiodic acid is 0.20, so that means we had an increase of 0.2 for our hydroiodic acid. And the change is a stoichiometric change. So if we look at the balanced equation, for every 2 moles of hydroiodic acid we produce, 1 mole of iodine and 1 mole of hydrogen must have been consumed. So half of 0.02, or 0.2, is 0.1 and 0.1. So at equilibrium, we're going to have 0.4 and 0.4 of both our hydrogen and our iodine. So now let's write our K expression. K equals the concentration of hydroiodic acid squared over the concentration of hydrogen times the concentration of iodine, and we'll plug in our numbers. So 0.2 squared over 0.4 times 0.4 will give us an equilibrium constant of 0.25. Now let's look at another problem. Okay, here it says at a certain temperature 4.0 moles of ammonia is introduced in a 2.0 liter container, and the ammonia partially dissociates by the following equation. So we've got ammonia breaking down into nitrogen and hydrogen. It says at equilibrium, 2.0 moles of ammonia remains in that 2.0 liter container. Calculate the value for K. So again, we've got the same steps. We're going to write our K expression, we're going to fill in our ICE chart, and then we're going to calculate K. So our K expression will be K equals the concentration of nitrogen times the concentration of hydrogen cubed over the concentration of ammonia squared. Now this problem is a little bit different because it doesn't give us the concentrations, it gives us the moles and the liters. So for our ammonia, we've got 4.0 moles in a 2.0 liter container, which is going to be an initial concentration of 2.0 molar. It doesn't mention the nitrogen or the hydrogen, so they are each 0 initially. And the other piece of information that the question gives us is at equilibrium, we've got 2.0 moles in 2.0 liters for our ammonia. So that's going to give us a 1.0 concentration of ammonia at equilibrium. So our change is 1.0 for our ammonia. Now when we look at the balanced equation, it's a 2-to-1 ratio to nitrogen. So that means that 0.50 molar nitrogen is produced. And then this is a 1-to-3 ratio. So 1.50 molar nitrogen or hydrogen is produced. So at equilibrium, 0 plus 0.5 is going to give us 0.50. 0 plus 1.5 will give us 1.50. Now we have our equilibrium values, we can calculate K. So we wrote our expression up here. We're going to plug in our numbers. 0.5 times 1.5 cubed over 1.0 squared. And that's going to give us a value of 1.7. Now let's do one more problem. This time we're given K. It says at a particular temperature, K equals 1.00 times 10 to the 2 for the synthesis of hydroiodic acid. It says in an experiment, 1.0 moles of hydrogen, 1.0 moles of iodine, and 1.0 moles of hydroiodic acid are introduced into a 1-liter container. We want to calculate the concentrations of everything at equilibrium this time. Now, an easy part of this problem is that it's giving us the moles of everything, and it's a 1-liter container, so the moles will equal the molarity. And what we're going to want to do is make our ice chart. So in this case, we are synthesizing hydroiodic acid, so we're going to have our hydrogen and our iodine and our hydroiodic acid. We've got our initial information, the change, and our equilibrium information. So for our hydrogen, we're going to have 1.0 molar. For our iodine, we're going to have 1.0 molar. And for our hydroiodic acid, we're going to have 1.0 molar. But it doesn't give us any of the equilibrium concentrations so that we can determine the changes. So if we don't know something, we're going to put in X as our value. So X amount of hydrogen is going to react. X amount of iodine is going to react. And since when we look at the balanced equation, hydrogen plus iodine gives us hydroiodic acid, and it's a 1:2 ratio to hydroiodic acid, we're going to be producing 2X of hydroiodic acid. So at equilibrium, we're going to have 1.0 minus X, 1.0 minus X, and 1.0 plus 2X. So it's going to be a little bit more complicated a problem. We've got K equals the concentration of hydroiodic acid squared over the concentration of hydrogen times the concentration of iodine. We're given K this time. 1.00 times 10 to the 2. For our hydroiodic acid, we're going to plug in 1.0 plus 2X, which has to be squared. And for our hydrogen and our iodine, we're going to plug in 1.0 minus X for each of them. So to kind of shorthand that, we're going to write 1.0 minus X squared. Now, we could make that a really hard algebra problem, but what we also could do is if we take the square root of both sides, that will make our problem a little bit easier. So what that will give us then is 10 equals 1.0 plus 2X over 1.0 minus X. Now we're going to multiply both sides by, we're going to multiply both sides by 1.0 minus X, and that's going to give us 10 minus 10X equals 1.0 plus 2X. We're going to add 2X or 10X to both sides of the equation, and that'll give us 12X. We're going to subtract 1.0 from both sides, and that's going to give us 9. We're going to divide both sides by 12, and we're going to solve for X. X is going to equal 0.75. But just because we solved for X doesn't mean we answered the question. The question wants to know what are the equilibrium concentrations. So for hydrogen, and iodine, they're both 1.0 minus X, which is 0.75. So their concentrations are going to be 0.25 molar at equilibrium. And when we look at the concentration of hydroiodic acid, it's going to be 1.0 plus 2X, which is going to give us 2.5 molar. And then what we could do is we could take the concentration of hydrogen and iodine and the concentration of hydroiodic acid and plug it back into the original K expression and double check that it adds up to 1.00 times 10 to the 2. And it does.